Okay, we are at section 20.4, generators, but before I get to the PowerPoint slides, I'm going to run a few simulations. First off, we're going to run a the no, that's not the one I want. I want to show the field. We're going to run a generator with a fet.colorado.edu simulator, and we're going to, you have a magnet tied to a little wheel. Think of it as like a water wheel, and we're going to turn on the water, and we'll turn it on slowly. And you can see that as the magnetic field sweeps around in the presence of the coil, you get a voltage. You get an induced voltage in the coil because of the presence of the changing magnetic field. And we turn the water on a little higher, and it's going to the voltage is going to change that much quicker. And we turn it full blast, where it's going fast. You can see the magnetic field is changing in the presence of the coil, and we're getting this voltage back and forth. So if you were to plot it, it would be like a sinusoidal waveform. Now we're going to switch to Walter Fent, and let's see if I have the right one. Yeah, okay. So this one uses water to generate the movement, and this one uses a little hand crank. And as you turn the hand crank, let's well, we don't have to start over it. You can see the sine wave. We can slow it down, and you can see that the voltmeter goes positive, and then it goes negative slowly. And again, if we speed it up, you'll see that the voltmeter goes back and forth much faster. Now, notice that this produces a sinusoidal figure. Let's put a commutator in there. The commutator breaks it up so that it's always going positive. You can see that if you look at the voltmeter, it's always a positive going signal. And so you put a capacitor and some leveling circuit, and you'll get a DC voltage out of this. So just as we can use some water to turn the water wheel, or we can use a hand crank to generate electricity, we can do the reverse. We can use electricity in the current going through a magnetic field will produce a force which will produce a torque on this loop, and it gives us a motor. So we've gone from generating the electricity to using the electricity to give us mechanical motion. We've gone from mechanical motion to electricity. Now we're going electricity to mechanical motion. It's just a transfer of energy type. So now that we've got that little discussion, let's go to the PowerPoint, and let's see. I lost the PowerPoint. Oh, there it is. I just have to start it and back up to where I need to be. We did motional EMF. Now we're at now we're at generators. So you saw the simulations, the moving simulations. Now we're going to have the static PowerPoint. So an EMF is induced in a coil which rotates by some external means in a magnetic field, whether it be water, whether it be a hand crank, wind power, anything that can turn a magnet in the presence of electric wires, or move a wire in the presence of a magnet, you will generate electricity, and you'll get this sine wave. Unless you have a commutator, and you'll get DC. So here's the inside a hydroelectric power plant where there's probably a dam, and so the water is, there's plenty of water to turn these turbines, and these turbines turn these coils of wire in the presence of these large magnets, and it generates electricity. And we're going to come up with the EMF. We know that E is equal to BLV, the magnetic field times the length times the velocity. Oops, wrong way. Well, we've got two of them. We've got a part of the coil going over here, part of the coil going over here. And so E is equal to 2 BLV that's perpendicular. So that's 2 BLV sine of theta. You can see that the sine of theta is over here. They've got it reproduced over here. Sine of theta. So V is equal to R omega, where omega is the angular velocity, V is the tangential velocity, omega is the angular velocity. So the tangential velocity V is equal to R omega. Well, what is R? R is this length A. R is A over 2. So V is equal to A over 2 times omega. So E is equal to 2 BL A over 2 omega sine omega t. And that becomes BLA omega sine theta. And L times A is the area of this coil. E is equal to N being the number of turns, B A omega sine omega t. And the E max is when sine omega t equals 1. So the max is NBA omega. All right. And here's a generator that has a commutator, and you can see that it only has positive going signals. Again, just like we saw in the Walter Fent demo. If you rectify these, you can come up with a nice DC signal. Now, if we turn things around, you can produce a motor. I showed you that with the Walter Fent. We don't have a slide for showing a motor. What we have here is we have how you can represent a motor, because whenever you've got this changing magnetic field, remember you have by Lenz's law, you're opposing that changing magnetic field, and that produces a back EMF. So here they're simulating it, or not simulating it. They're showing it as the power to the motor, and it's a 10 ohm coil resistance, the coil that makes the windings of the motor, and it produces a back EMF of 70 volts. So essentially what you've got is a 50 volt. You get the difference. You get the applied voltage in the back EMF, or 50 volts in this case. The current is always reduced by the back EMF. When a motor is turned on, there's no back EMF initially, and the current is very large because it's limited by the resistance of the coil. It's limited only by the resistance of the coil. As the coil begins to rotate, the induced back EMF opposes the applied voltage, and the current in the coil is reduced. If the mechanical load increases, the motor slows down, which decreases the back EMF. This reduction in the back EMF increases the current in the coil, and so also increases the power needed from the external voltage source. As a result, the power requirements for starting a motor and for running it under heavy loads are greater than for those for running the motor under average loads. Um, okay, and I think that's it for this. Next 20.5, we're going to go to self-inductance.